Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. So you have a circuit that you want to simulate using LTSpice. And, well, maybe you have a potentiometer that you want to include in the design, and you want to simulate the circuit with different settings on the potentiometer. On the other hand, you might want to see what the effects are of the tolerances of the values of various components in the circuit. You want to develop a worst-case scenario. Then, in both of these cases, this is the video for you. In this video, I will show you how to have LTSpice automatically step through the selected values and show the results in your simulation. If you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. Now, I've placed helpful links in the description for you, which include a link to a zip file which contains all of the LTSpice models and the Excel spreadsheet I use in this video. So let's take a look at the easiest one first. Well, the quickest and easiest way to do this is using the .step command. Yes, this is the easiest, but it's limited to no more than 3 components. So you can step through values in various ways. You can provide your own list of values. You could give it a starting value and an ending value and a value to increment by. For example, you might want to start with a value of 1 microfarad and end with a value of 2 microfarads. If you step through using an increment of 0.1 microfarads, then it will simulate the circuit using 1 microfarad, 1.1 microfarads, 1.2 microfarads, and so on, all the way up to 2 microfarads, if you choose the linear method of stepping. On the other hand, you could do a similar thing using an octave or decade method. Now, with this one, you have to choose the number of points per octave or per decade. So you ask, well, what is meant by an octave and a decade? That's a good question. An octave is just like in music. The frequency of middle C is 261.63 Hertz. 1 octave up to the next C is 523.26 Hertz, exactly twice the frequency. In terms of electronics, 1 octave up from 1.5 megahertz is 3 megahertz, and 1 octave up from that is 6 megahertz. Decades, well, that speaks of powers of 10. So from 1 to 10 is 1 decade. From 10 to 100 is another, and so on. Now, I have one last point for you that's very important to know. If you specify stepping through 3 values on 1 component, you'll get 3 plots, 1 for each value. Now, suppose you step through 3 values on 1 component and 4 values on another component. LTSpice will step through every value of 1 component for every value of the other component, giving you 3 times 4 or 12 traces to view. Now, I will cover how to utilize all of these traces a bit later, but first, the mechanics of creating them. So here's my example, the amplifier circuit I used for the microphone project. The question I'm asking myself, what effect does the tolerance of the feedback elements R4 and C2 have on the frequency response of the circuit? Now, I'm only interested in the extents of the tolerances and the nominal value, so I'm going to use a value list which contains these 3 values for each of the 2 components. The first step in this process is replacing the component values with PSpice parameters, or what we might call variables. I will start with the resistor. I will right-click on it and replace the value with a parameter name enclosed in curly brackets. This is the feedback resistor. So I'm going to call it FR, feedback resistor. So left curly bracket, FR, right curly bracket. I will do a similar thing with the feedback capacitor, calling it FC for feedback capacitor. Now we have to create the dot step statements the easiest possible way. Either hit the S key or click on the .op icon on the toolbar. Type .step in the field and hit enter. Now the cursor is dragging the .step text around the schematic. Click on a spot and deposit it. Now right-click on it and a nice .step statement editor dialog box opens. In the name of parameter to sweep field, I will type FR for our feedback resistor. In the nature of sweep field, I will choose list from the drop-down list. In the first value field, I will enter the value of 160K minus 1%, which is 158.4K. In the second value field, I will enter the value of 160K plus 1%, which is 161.6K. In the third value field, I will enter the nominal value of 160K. Now, in this dialog box, you are limited to just 3 values using the fields provided, but you're not actually limited to just 3 values. If you click in the field at the bottom where the command is being created for you, you can continue to add values to this list. Now, we click on the OK button. We repeat this process for the FC parameter. Once done, we just click on the Run icon and watch it build our simulation results. To see the results, we click on the signal of interest, and I'm interested in V out, so I will click on that spot in the schematic. And here are the results. You can see the multiple traces, each indicating the results from a different combination of the values that you specified. But what if you have a lot more components that you want to step? I mean, we look at this circuit and we have a total of 7 components that can affect the overall frequency response of the circuit. And all of these have tolerances associated with them. So what do we do then? Well, now it gets a bit more complicated, but we can do this. As a note of source, I discovered this whole process in the technical document found at the link that I've placed in the description. This is far more complex than the previous process, but it will step through every component you choose to step and provide the results. The process I'm going to describe here is designed to test the effect of the tolerances of all the components in a design. As such, you are limited to only 3 values for each component: the lowest value, the highest value, and the nominal value. Now, it will simulate every possible combination of the maximum and minimum values of every component you specify. Then, in one last run after this, it will simulate the results of the nominal values alone. The total number of runs can be calculated using this following formula. The number of runs is equal to 2 brought to the nth power plus 1, where n is the number of components that you've chosen to step. Now, this is important to remember. You're going to need it later. This will require us to define some pretty special PSpice functions and assign some pretty funky looking values to our components. So hang on, here we go. Well, the first step is to define our required PSpice functions. If you look down in the description, you'll find these functions for you, so you can just copy and paste. Now for the first one, either type the S key or click on the .op icon in the toolbar. and then copy and paste that massive function into the field. Then we click on the OK button, and now your cursor will be dragging this text around your schematic. Click on a spot somewhere and place it in your schematic. We get to repeat this process with a second function. With these in place, we have to determine the components that we're going to be stepping. Well, in the case of my example, C1, C2, C3, C4, R3, R4, and R6 all affect the overall frequency response of the circuit. This gives me a total of 7 components that I want to step. Now, all of the capacitors are 10% capacitors, and all of the resistors are 1% resistors. Now, I will establish some variables for these tolerance values by creating the following PSpice directives. The first one is .param.param, and then TOLA is equal to 0.1. This is tolerance A, and it is 10% or 0.1 in decimal. Now, I'll use this with all of my capacitors. And then there is .param.param, TOLB, is equal to 0.01. This is tolerance B, and it is 1% or 0.01 in decimal. I will use this for all of my resistors. The last couple of PSpice directives that we have to define set up the stepping parameters for our simulation. Well, now I have to bring back to your memory that we have 7 components that we're going to be stepping. Also remember that the number of runs that have to be made is equal to 2 brought to the nth power plus 1, where n is the number of components that you've chosen to step. So with 7 components, this becomes the number of runs is 2 brought to the 7th power plus 1, which equals 129. But the first step is 0. So counting from 0, a total of 129 steps, means that our last step is step number 128. Now, with this in mind, we need to create the following PSpice directives. .step param, P-A-R-A-M, run 0, 128, 1. And then .param, numruns, N-U-M-R-U-N-S, equals 128. Now, with all of the PSpice directives put in place, we need to assign values to our components. Every component has what is called an index value for this process. The first component has the index value of 0, the next is 1, the next is 2, and so on. This is important to remember as we enter the value for each component. The syntax that we have to use is this: left curly bracket, WC, this is the function defined earlier, left parenthesis, followed by the nominal value of the component and a comma. Next is the tolerance, followed by a comma. Now we've defined TOLA and TOLB to use for the tolerances. Then the index number for the component, which is unique to this component. We follow all this with a right parenthesis and then a right curly bracket. Now, I'm going to start with C1 as index 0. then R3 is index 1, and so on. Now that I have all my component values assigned, we are ready to simulate the design. We click on the Run icon on the toolbar, and then watch the lower left-hand corner of the window as the simulation proceeds. When it is done, we can click on the spot of interest. Well, in my case, that's V out. Well, there are two ways to examine the data you have now acquired with LTSpice, and the first is from within LTSpice itself. In our example, we are looking at a total of 129 traces. Well, like with any simulation, you can zoom in and out at will. You can create your own cursors and make measurements. The trick here is knowing what you're measuring. If we click on our output variable to enable a cursor, we can drag this around just like we always did before. Now, to move from one trace to the next, you use the up and down arrows on the keyboard. But how do you know which one of the 129 simulation runs you're actually looking at? Well, once you've positioned your cursor where you want it, right-click on the cursor position and a window will pop up telling you which run this belongs to. Suppose you only want to view the data from particular runs. So how do we select what we're seeing on the plot window? Maybe we don't want to look at 129 different runs. We only want to look at certain ones. Well, right-click on the open place in the plot window, hover over the View entry in the pop-up menu, and then select Steps from the submenu. A dialog box appears to allow you to choose which runs you want to see and which you do not. Unfortunately, they do not indicate which component values are associated with each step. So I'm going to select run 129 because this is the nominal run. And then I'm going to select the top and bottom runs of what I see on the screen. And there's an alternate way to accomplish this using Excel or a similar spreadsheet. Well, the first step in using a spreadsheet is to export the data to a text file. To do this, we select the plot window, then click on the File menu item, and select the Export Data as Text from the drop-down menu. Select the destination and what you want to export and click on the OK button. Now we get to go to our spreadsheet to import the data. So we open Excel and then open the text file. Now this is a delimited file. As delimiters, select Tab, comma, and Other, and then enter a left parenthesis in the Other field, and then click on the Finish button. The data as imported is organized in groups with the groups stacked on top of each other vertically. Each group is a separate run. In this simulation, I have 500 data points per run. I used Excel formulas to extract and organize the data for each run side by side. Then I used the max and min formulas to extract the extents of the response for any given frequency. Now I know that the last run, run 128, which is actually the 129th run because we started at 0, contains the response with all of the nominal values, so I include this one as well. With this in hand, I can plot the extents of the response given all of the tolerances of all of the components that affect the response. I have included this spreadsheet in the zip file whose link is in the description. Now you have everything that you need to step through component values in a simulation to see what effect that they might have on the performance of a design. If you found this video helpful, please click on the like and don't forget to subscribe to the channel. Thank you so much for watching. Until next time, Toodle-Oots.